In this video, we'll be talking about Maxwell's equation with sources. Before we considered it in vacuum, but now we will consider it with sources. And by sources, it means electric charge or electric current, or even though it doesn't exist, magnetic charge or magnetic current. So hopefully there's not too much background noise. There's a little bit of construction being done above me. So hopefully it's not too bad, but let's go. So just recall that you have the vacuum. If I can get the correct amount of lines. The vacuum version of the equation, which is just the gradient of f, is 0. And also, then, or not also, then when we have sources, end up gradient of f equal to j. So this j has an electric an electric source and a magnetic source. Note that this source equation is not invariant under the global phase map, where you take f and you map it to some phase I theta f, because when we covered this before, we saw that this equation is invariant under this mapping. However, this equation is not. This will be talked about more later in the paper, so I'll cover it in a later video. Taking the gradient of the source equation, that the gradient of f, or gradient squared of f, is equal to the gradient of j and this implies two separate equations. So this implies one, which is that the gradient of f here is equal to the curl of these fields, of these source fields. And this is the same thing as saying that the divergence of JE is equal to the divergence of JM, which is equal to 0. This is a wave equation. And this below thing is called a continuity equation. So a continuity equation in physics, like this, basically states that when you move, you're not going to suddenly create charges or destroy charges. So this is the space-time gradient, so it has change in time and change in space. Basically, it says as you move throughout space and time, you're not going to suddenly create anything. So this is 0. If you had charge either suddenly created, you would have a positive value. if you had charge suddenly destroyed, you would have a negative value here. So it's good that you don't have, or it's good that you impose this to say that you're not creating or destroying charge. And then because you're not creating nor destroying charge, you can use the wedge up here for the wave equation. We can take the space-time split. Relative to gamma naught. And this is, have the gradient E plus BI equal to gamma naught C rho electric, then the electric current density. So you have electric density, charge density, then you have electric current density, which is charge changing per time, then plus naught. Then you have the magnetic equivalent. I do want to emphasize that magnetic charge does not exist, or rather, every single test that we have done says that it does not exist. And so it existing would be a statistically severely unlikely thing, so I'm just going to say that it doesn't exist. I don't know. I'm so emphatic about that because there are some people who are like, well, it could exist, and it's like, well, also flying pigs could exist, but they don't. So, or no one's ever seen them. It's just not good logic for scientists to have. So this becomes, we can expand this out. So this can have a gamma naught on the outside here. And this is as so, E plus B I. And you, of course, get this right here. So if they both have a constant of gamma out front, you can get rid of it. So this becomes, it just becomes this. Plus this. And then we can expand this out. Oh, I don't need that. Expanding this out just gives partial naught E plus partial naught B I plus divergence of E plus divergence of B plus the, or here, hang on, what would it be? Yeah, no, plus the curl of E I plus, or sorry, minus curl of B. The I that shows up here in the curl cancels with the I on the B, so you get a negative sign. Then equal to C rho E minus vector JE plus C rho M I minus J M vector I. And then we can associate every term here with one of Maxwell's four equations. So if we have 1, 2, I'm going to say, actually, I'll just do this. So the divergence here, this is Gauss's law. So I'm going to put GL, Gauss's law. This is also Gauss's law. These are both the only scalars in the entire equation. And then this be no magnetic monopoles law. And this will be counterintuitively the no magnetic monopoles law, because we know this is 0, but this corresponds to this. Because it's this is the only quadravector, this is the only quadravector, so they have to be equal. Then the only vector terms, this is a vector term, and this is a vector term, and this is a vector term. So this must be the Ampère-Maxwell law. Maxwell law. And then that just leaves the last little bit, which is Faraday's law. Oh, or is it the other? I can never remember. Is it Faraday's law that's change in time of magnetic field? I'm pretty, yeah, change in time of magnetic field is Ampère-Maxwell, because Maxwell called this the displacement current, because he thought it was displacing the ether, but it wasn't. It's not. The ether doesn't exist. Okay, so this is then Faraday's law. Faraday's law. Faraday's law. Cool. So then the Maxwell's equations just become writing out Gauss's law. Divergence of E is equal to C rho E, the no magnetic monopoles law, which is seemingly being broken here because there are magnetic monopoles. Is this, then get Faraday's law, dV plus curl of E equal to minus J M. You'll notice that I'm just ignoring the i's because everything here has a factor of I, so I'm just ignoring it. Then partial of E minus the curl of B is equal to minus JE. So you get Maxwell's four equations from this when you put it in a space-time split, relative to this direction, of course. I don't know, that's a satisfying derivation. I've always thought so, and I always will. So we'll now consider that for potentials. We'll now consider the split for a potential Z equal to AE plus AMI. However, I will only give the analysis for AE because the math is the exact same for AM, and I don't want to write it twice. If you can do this, then it's the exact same for this. You just change the subscript and you add an I. So, you have this equal to the Laplacian of Z. But if we're only considering one component, then we just need to consider the Laplacian of AE. which the Laplacian of AE is equal to JE. So we only have to look at electric terms. This is just when we do a space-time split here, we get to the Laplacian phi e plus a vector gamma naught equal to c rho e plus j e gamma naught. So we have these two things, which then, again, there's a factor of gamma on both sides, so we can cancel. This implies that you have two equations, or if this cancels, then you're going to only have the Laplacian of a scalar giving you a scalar, and then the Laplacian of a vector giving you a vector. So the Laplacian of phi e is equal to c rho e. And you get that the Laplacian of A is J E. So you get two coupled wave equations that describe how charges and stuff move relative to a potential.